so today we're going to talk about area of rectangles, and I believe this is maybe our historic day. Yes, today's a historic day in that we're going to learn the last of all the postulates for this entire book. After this, everything that we have has been proven. Remember, postulates we just accept to be true. So our objective, if we could get into black, would be good. Today is going to be understanding postulates, and we've got one theorem regarding area of rectangles. And this comes out of lesson 11.1. Remember the last lesson we did, that's part of chapter 11, was actually from chapter 10. All right, so postulates. Let's start with postulate 17. And postulate 17 states that the area of a square is the square of the length of a side. A equals s squared. So in the theorem, this postulate, they tell us the formula. That's why you don't get to use your theorem cards on quizzes and tests, because I need you to memorize these. Okay? So that's the first one. The next one, postulate 17, or 18, excuse me, actually has a name. And his name is the area congruence postulate. And this one states, if two figures are congruent, and remember with congruent figures that means their measurements of their sides are equal to each other and all of their angles have the same measurement, then they have the same area. Okay, and that's very reasonable sounding. That's nothing earth-shattering. Okay, and then we've got the last, sad but last postulate, number 19. It also has a name. And this one's called area addition postulate. You've actually used area addition postulate when you were given a weird looking shape and then you try to break it into recognizable shapes like rectangles and squares and whatnot, and then you figured out the area of each of the pieces and you could add them together to figure out the area of the original weird shape, since there is no formula that fits that weird shape. So you've done that back in probably 5th, 6th grade. You guys dealt with that idea. So the area of a region is the sum of the areas of its non-overlapping parts. Remember when you were doing this before, the different shapes, they together made the original shape, but they no shape overlapped a different shape. Now, I probably can't fit it here, but I want to do a diagram of this. And please don't think, because we will be talking about this shape in a couple days, don't think that this is the best way to figure out the area of the following shape. Okay, everybody good? Can I move? Yes? Okay. So to kind of illustrate that postulate 19, the area addition postulate, let's say we have this shape. What shape would you say he is? Trapezoid. But let's say that we don't know how to figure out the area of a trapezoid. Okay, so what we could do is break it into other smaller shapes that I do know the formula for. So I could break it into 2 triangles and a rectangle. So we could say that the area of the overall shape, that ABCD, and this may have been an exercise that you guys did in elementary school when you didn't even know how to figure out the area of a trapezoid. So it would be the area of the first sector, 1, plus the area of the second sector, 2, plus the area of the third sector, 3. And that would be the area of the overall shape. Okay. Now, I am going to give you some vocab, and because instead of, what's the traditional formula for area of a rectangle that you guys learned? Length times width. So we are now going to switch gears, and you're not going to see length times width anymore. We're going to use other words, and Hannah, I heard you use them. Base and height, because we have several different formulas that use that same notion of base and height. So we keep it more uniform with our formulas when it comes to geometry. So first thing we need to know is what is a base. And base is the letter B, signifies what a base is. And technically, a base is any side of a rectangle or parallelogram. Now, what have you guys always called the base? The bottom, right? That's what you've always associated the bottom with. But again, the base is only a base if it has a second component to it. Okay, so we'll get into that. Next is that second component, and that's called an altitude. Oops, sorry. And we've talked about altitudes before. So here's the key for us now. It's any segment perpendicular, okay. I don't know what my spelling issue is today, but it's bad. Perpendicular to the line containing the base from base from any point on the opposite side. So notice this definition is different than the one from the triangle because the altitude had to come from a vertex and it had to be perpendicular to the opposite side. This one is saying, hey, this is any segment that's perpendicular to the line containing the base. And the reason why they say that is sometimes where that line falls in order to be perpendicular, falls outside the shape. Just like we've had that with triangles, where sometimes we would have an altitude that's outside the shape. Because the key is it's not necessarily perpendicular to the base, but it has to be perpendicular to the line that that base is on. So we can actually go outside a shape with an altitude. Now, we don't use the altitude in any calculation, contrary to popular belief, because an altitude is an object, and I can't multiply objects. So what I need to do is to figure out what the measure of an altitude is, and that's what we use in our formulas. And what do we call the measure of the altitude? What's that called?
Height.
That's called height. So height is used the letter H, and it's the length of an altitude. Okay. Now that we have that background information of a base is a B, and it's any side of a rectangle parallelogram, and that altitude is any segment perpendicular to the line containing the base from any point on the opposite side, and height is the length of an altitude, now we can get into our first theorem for this chapter. And that is Theorem 11.1, which does not have a name. And Theorem 11.1 says the area of a rectangle equals the product of its base B and height H. And then it says in parentheses A equals BH. So gone is the LW for the area of a rectangle, and now comes in the B and the H. So what I'm going to do is actually, let's do some practice and we'll do a proof afterwards. So one thing to keep in mind about area. Area has certain dimensions, and if we don't have the units right, then we're not actually demonstrating area. So area is always measured in square units. So meters squared, feet squared, inches squared. That's what it looks like, but we actually read it as square meters, square feet, square inches. The other way to write it, square miles. So SQMI for the abbreviation of miles. So we're going to do just a couple practice problems and then add in a formula or a proof. So find the area. And in number 1, you're told that you have a rectangle with a base of 3.5 centimeters and a height of 2 centimeters. So that fits into our formula really easily, where we have the area is going to be the length of the base times the height. So we're going to get 3.5, and I'm going to keep labels in here so you can see 3.5 centimeters times 2 centimeters. Well, 3.5 times 2 is 7, and centimeters times centimeters means I get 2 of them, so that's where I get the square unit. When I'm multiplying, I add exponents. So there's your answer, is 7 squared centimeters. Okay. Second one. What if I asked you to find the area of this shape? And we're told this is 8, this is 5, this is 6, and that left side is going to be 2. So we've got a couple options what we could do. Option 1 would be cut it this way. Look on your right side. I know one portion of it is 2. I know the whole length of that side is 5. So what would this piece be? This piece would be 3, right? 3 plus 2 is the same as 5. So at the top, I would have a rectangle that's an 8 by a 3. And at the bottom, I have a rectangle that is a 6 by a 2. So that would give me 24 plus 12, which equals 36. And I don't know why I have such problems writing my 3's. Now, I want to share with you another way that people don't often think about. So I'm going to erase the marks in my diagram. This is called area model by subtraction. Okay. What if we created one big rectangle by doing this? Now, that little green square doesn't exist, or that little green piece doesn't exist. So if I can figure out what its dimensions are, then I could take it away from that big rectangle that I formed. Because I know what the big rectangle is. What are the dimensions of the big rectangle?
40.
No, dimensions. 8 times 5. Okay? So now we're going to figure out the dimensions of the small guy. We'll already know what one of the dimensions is. It's 2. But now we need to know one of the horizontal dimensions. So I know it's 8 across all the way. And at the bottom it shows me to that portion is 6. So what would be the leftover piece? 2. So this is a 2 by 2 box. So if I took that away, then that would give me the 40 minus 4, which gives me the same answer of 36. So, and then I could have also drawn this with a vertical line, right? Over here, I could have done this as well and figured it out that way. So there's more than one way to solve these area problems when the shape is not a stereotypical shape. Okay? All right. That gives me enough time, yes? Yeah. All right, so we got a little proof to do. Proof-de-duty. So we want to actually prove out Theorem 11.1. So we're going to be given a rectangle with base B and height H. And our job is to prove that its area would be A equals BH. So that means, since we're proving this theorem, we can't use it in there. So let me draw a picture. Actually, that's too big of a picture. And here's our guy, base of B, a height of H. So the only things that I have that I can use that relate back to this is I know the area of a square, and I have, if two figures are congruent, then they have the same area, and the area of a region is the sum of the areas of its non-overlapping parts. So those are the only things that I could potentially use in this particular drawing. So what I'm going to do is make this rectangle become a square. How? Well, I'm going to draw some auxiliary lines. And I'm going to draw these auxiliary lines, which look really lousy. That looks a little better. So that this piece is H by H. And I'm going to draw this down here, so he's the length of B. So basically what I'm doing is now creating a new square whose dimensions are B plus H. Okay. So that makes him B, him H, him B. Okay? So, statement reasons. We are going to draw auxiliary lines. To form larger square as shown. And it's funny because I actually have written down here postulate 6, but I don't think that's accurate. I think what really is appropriate here would be ruler postulate, right? Because I want to draw a segment that exactly measures H, and I want to draw segments that are exactly B. So to me, that's more of a ruler postulate because I'm using exact lengths. Okay, one of the rare times ruler postulate actually comes into play. Okay. Now, from the postulate 17, I know what the area of the big square is. And also, I know what the area of the big square is through postulate 19. So, for example, let's put some information in here. What we're trying to figure out is what this area is. Because remember, our formula is supposed to be A equals B times H. What is the area of this piece down here? So the B by the B. He's going to be B squared. What's this little guy up in the upper right? H squared. And what would be this piece off to the side? Oh, he's another A. Because he's just a mirror image of that rectangle on the top. Cody, you have a question? Okay, you always rest your hand over your face? Okay. This is checking. So what we're going to do is write two different ways for the area of this square. So let's do it area big square equals, well, there were two A's. There's a B squared and an H squared. That is using that area addition postulate. Using the formula from postulate 17, we could say the area of the big square is equal to the length of the side squared. Oops. So that would be area of a square A equals S squared. So now I have two things that equal the same thing. Now remember, my answer is supposed to have A on the left, so I'm going to take the first area that is of the big square and put it on the left. And then put the quantity H plus B squared over here. So that's just going to be substitution. Property of equality. Okay, now what I'm going to do is take the right side, and I'm only doing math on the right side, and I'm going to FOIL it out, or multiply it out, and I get H squared, I get HB, and HB is 2HB, and B squared. So all I did was distributive property of equality. So remember, my job is to get A alone, so I'm going to subtract B squared from both sides, and I'm going to subtract H squared from both sides. And I get 2A equals 2, and actually I'm going to rearrange these letters, I just realized now. These should be BH. Why do they need to be BH? Because that's what the formula has, right? So that's subtraction property of equality. And last but not least, divide both sides by 2. Because I'm doing math on both sides, it's a property of equality. So that's division, hello, English. property of equality. And that's how we prove what the formula for the area of a rectangle is.